t-SNE in machine learning. AI intermediate level. Introduction. Modern machine learning datasets often contain high-dimensional data with many features. Examples include image datasets with thousands of pixel values, text datasets with thousands of word embeddings, genomic datasets with thousands of gene measurements. Understanding patterns in such high-dimensional datasets can be difficult. To visualize and analyze these complex datasets, machine learning uses dimensionality reduction techniques. One of the most powerful visualization techniques is t-SNE. t-SNE stands for T-Distributed Stochastic Neighbor Embedding. It is mainly used for visualizing high-dimensional data in 2D or 3D space while preserving relationships between data points. tSNE is widely used in areas such as deep learning feature visualization, natural language processing, image clustering, recommendation systems, bioinformatics. Understanding t-SNE helps learners explore and interpret complex machine learning datasets visually. What is t-SNE? t-SNE, T-Distributed Stochastic Neighbor Embedding, is a dimensionality reduction technique designed for data visualization. In simple words, t-SNE equals converting high-dimensional data into 2D or 3D while preserving local relationships. Example concept. High-dimensional data means t-SNE means 2D visualization. t-SNE attempts to keep similar data points close together in the lower dimensional space. Why tSNE is important. High-dimensional datasets are difficult to visualize and analyze. Example concept. Many features means difficult to visualize. t-SNE helps visualize complex datasets, identify clusters in data, understand hidden patterns, explore relationships between data points. This makes t-SNE extremely useful for exploratory data analysis. How t-SNE works. t-SNE works by preserving pairwise similarities between data points. Example concept. Similar data points means remain close in visualization. Steps involved. Measure similarities between data points in high-dimensional space. Convert these similarities into probability distributions. Map data points to lower dimensional space. Adjust positions to preserve similarities. This process creates a visual map of the dataset. Local versus global structure. t-SNE focuses on preserving local structure. Example concept. Nearby points means remain neighbors. This means clusters are preserved well. Similar samples stay close together. However, global distances between clusters may not always be perfectly preserved. tSNE versus PCA. tSNE is often compared with another dimensionality reduction technique called PCA. Method purpose. PCA reduce dimensionality while preserving variance. t-SNE visualize data while preserving local structure. Example concept. PCA means linear reduction. t-SNE means nonlinear visualization. PCA is often used before t-SNE to reduce initial dimensionality. Key parameters in t-SNE. tSNE has several important parameters. Perplexity. Controls the number of neighbors considered. Example concept. Low perplexity means focus on local patterns. High perplexity means broader neighborhood. Typical values range between 5 and 50. Learning rate. Controls how quickly the algorithm adjusts point positions. Example concept. Small learning rate means slow convergence. Large learning rate means unstable mapping. Choosing an appropriate learning rate improves visualization. Number of iterations. Controls how long the algorithm runs. Example concept. More iterations means better convergence. Higher iteration counts often produce clearer visual clusters. t-SNE visualization example. Example dataset. High-dimensional dataset. Feature 1, Feature 2, Feature 3, Feature 4. After applying t-SNE, X, 2D, Y, 2D, 1.2 to 0.5, 0.8 to 0.2. Example concept. High-dimensional dataset means 2D visualization map. Clusters become visible in the 2D plot. t-SNE workflow. A typical t-SNE workflow looks like this. Dataset. Down pointing arrow. Data pre-processing. Down pointing arrow. Optional PCA reduction. Down pointing arrow. Apply t-SNE. Down pointing arrow. 2D 3D visualization. This workflow allows analysts to visualize complex datasets effectively. Advantages of t-SNE. t-SNE provides several benefits. Advantages include excellent visualization of clusters, preserves local relationships, reveals hidden data structures, useful for exploratory analysis. Example concept. Complex dataset means clear cluster visualization. Because of this, tSNE is widely used in deep learning and data analysis. Limitations of t-SNE. Despite its advantages, tSNE has some limitations. Limitations include computationally expensive for large datasets. Global structure may not be preserved. Results depend on parameter choices. Example concept. Large dataset means slower computation. For very large datasets, other techniques such as UMAP may be used. Example Python code. t-SNE can be implemented using scikit-learn. Import the algorithm from sklearn. Manifold import tSNE. Apply t-SNE. tSNE equals tSNE. n underscore components equals 2. x underscore reduced equals tSNE.fit underscore transform. X. This converts the dataset into 2D coordinates for visualization. Real-world applications. tSNE is widely used in AI systems. Image recognition. Visualizing deep learning feature embeddings. Natural language processing. Visualizing word embeddings such as Word2Vec. Bioinformatics. Analyzing gene expression data. Customer analytics. Visualizing customer clusters. Fraud detection. Identifying suspicious transaction clusters. Concepts learned from t-SNE. Understanding t-SNE helps learners understand. Checkmark how high-dimensional datasets are visualized. Checkmark how local data relationships are preserved. Checkmark how clustering patterns emerge in visualization. Checkmark how dimensionality reduction aids data analysis. Checkmark how complex machine learning datasets are interpreted. tSNE is a powerful technique for visualizing high-dimensional machine learning data. Simple definition. t-SNE. T-distributed stochastic neighbor embedding. A nonlinear dimensionality reduction technique used to visualize high-dimensional datasets by mapping them into 2D or 3D space while preserving local relationships. Final summary. tSNE is a powerful dimensionality reduction technique designed for visualizing complex, high-dimensional datasets. By preserving local relationships between data points, t-SNE helps reveal hidden clusters and patterns in data. Although computationally expensive for large datasets, it remains one of the most effective tools for visualizing machine learning data and understanding model representations. Understanding tSNE is essential for anyone working with data visualization, exploratory data analysis, and machine learning interpretation.